So welcome back, everybody. This week we're going to talk about a topic that was introduced earlier, but we're building upon, and this is this idea of correlational research. So think of correlational as association, which is different from causality or cause and effect. We talk a lot in experiments about how the independent precedes the dependent, and we can control for internal validity or cause preceding effect, but here, we're talking about correlation, which is just association. Right, so we want to see, is there a relationship that exists? Are they associated? If there's an increase in one variable, is there an increase in another? So for example, we often say that if we increase education, we hope to increase income. So both of those variables are increasing at the same time. If we increase education, are we decreasing job burnout or job dissatisfaction, right? There's an inverse or different relationship. So again, correlation doesn't do cause and effect. It just talks about a relationship. And you can see that unlike an experiment, which is really ordering and testing a relationship, a preconceived or created relationship, correlation is just exploring what happens when this variable changes, what happens to the other. So what happens to B when there's a change in A? And I'm sure you all have heard of this term quite a bit, but correlations have positive or negative descriptions attached to them. So positive correlation, if you look here, right, it says that when A increases, B increases. A does not cause B, but we see that when there's a change in one, there's a change in another. So we could say that when you increase increase your cholesterol level, we also see that there's an increase in cardiovascular risk. Now, we may want to say that that relationship has a cause and effect, and there's an independent and dependent variable, but we cannot, right? Education increases, income increases, cholesterol increases, cardiovascular risk increases. Do you notice I'm saying increases? They increase at the same time, but I'm not saying they cause one another. So this is why it's exploratory. So a correlational study looks to see what variables are associated to have changed within a population. So correlational research to look at associations of variables, we say is about 30 cases or 30 people in the sample size. And it is hypothesis driven, although we're trying to look and see, is there an association? We're not predicting cause and effect. So we're just looking at association, even though there are hypotheses that are there. So if we think about public health research, which we do quite a bit, right? If we're in public health, that we're going to look at two diseases or two outcomes, right? In this case, we're looking at an exposure. So you can see that there were 3 different populations, A, B, and C, that were all exposed to this exposure 1, and then they've had an outcome. So each population had a different level of exposure, right? B got a heavy level of exposure, and B also had a high level of outcome. So we want to look at this attribute, and this attribute is only for populations. So if we say that if you're in population B, right, population B has a greater level of exposure and a higher level of outcome than population A or C, but we can't say that people in population B are all going to have a high level of exposure. So we can't go from the level of a population and then say somebody within that population is going to mirror that. And that's called ecological fallacy, right? That you could be an individual that comes from a country that has a high BMI or BMI score, but you could have a low BMI, right? So you, just because you're in population B, which has a higher rate of exposure and outcome than the others, doesn't mean that you yourself will have a higher rate or exposure. That's called ecological fallacy, generalizing from the population down to the individual level. And then you might ask yourself, so we talk about correlation, there must be some way we can quantify it. And guess what? There's Pearson's correlation coefficient. You see this little R, it's Pearson's correlation coefficient, or called Pearson's R. So you want to know both the degree of relationship and the direction of relationship. So the degree of relationship is between 0 and 1, but the relationship can have a direction of a negative relationship or a positive relationship. So as you get to these ends of 1, you know that that relationship is stronger. So a relationship of 0.5 is stronger than a relationship of 0.1, but a relationship of 0.9 is closer to 1, and therefore this has the most strength. But you can have a negative relationship or positive. So if A increases and B decreases, it's a negative relationship. Remember, if you know, increase respect for workers, right? Respect increases, burnout decreases, that's a negative relationship. You can have a positive relationship. Remember the cholesterol and heart disease, that, you know, there's this an association, a strong association between increase of cholesterol levels and increase of heart disease. So relationships can be positive or negative. As I just mentioned, the Pearson's correlation coefficient, affectionately called Pearson's R, or people say little r, right, which is completely fine. It tells you the strength. So someone might say, how strong is the relationship between heart disease, high cholesterol and heart disease, or increasing employee respect and lowering burnout? And this is just ranges, right? So if your score or your R value, your Pearson's correlation coefficient, you know, is almost 1, this is high, right? High, perfect relationship. If you have a very low relationship, it means that there's some relationship between these variables, but it's not strong or consistent. And here, if you look throughout all of these columns, you're going to see there's a strong relationship here with score, with IQ and GPA, right? This is a problematized relationship. We know IQ calculation, it can be flawed, but this is just to show you and give you an example. First of all, the R is high, it's positive, which means when one increases, the other increases. It's almost 1, which means it's getting close to perfect. And this would say that however we're measuring IQ, there's a direct relationship, a positive relationship. So as IQ increases, so does GPA, right? Here, there's no relationship. We have an R that's 0.13, so it's a low R value, but we see that there's no association. So here there's an IQ and someone has a higher weight. Here's someone who has a higher IQ with the lower weight. There's no trend in these data, right? There's no trend in these data. And that if you look at the strong negative, it's actually the reverse. So we're looking at IQ and ERAS. So we're saying that the higher the IQ, right, the lower the ERAS. So the relationship is, as IQ increases, your number of ERAS or percentage of making ERAS decreases, right? Higher IQ, lower number of ERAS. And the R value is strong, so it's a really strong relationship. In the real world, it's a little bit more messy and the R values don't really sync up, but this is just an example. So we're going to look at scatter plots, right? If you're like me or many people, we like to see data depicted visually. And so you can look at correlations by looking at how the line appears, how the correlation appears in the graph, right? So every dot looks at a pair of scores. And you're going to see where the line is, where the line appears in that relationship. And the more scattered the dots are from the line, the weaker relationship. So you can see here with an R of 0.94, we're getting to a perfection. This is a very strong, clear line. Moderate positive R is like midway, 0.44. We can see there's some directional line here, but a lot of people are veering off, right? A lot of relationships are veering off. I'm going to flip it. Oh, sorry, let me show you this. This is no relationship. A lot of people think it looks like abstract art. This R value is saying 0, 0. So there's no relationship at all between these variables. There's no really discernible line we can draw. So they're all over the place. And here's another way of looking at it with data. So IQ and GPA, you see there's that positive relationship. As IQ increases, GPA increases. Remember with weight, we had the example with weight. We see there's no clear line here. There's really no relationship, no association. And here there's a negative association. So with IQ increasing, number of errors decreases, right? So you can see this is a strong positive. Here's a negative association or correlation, and here's just nothing. And sometimes, you know, in the real world, the relationship between an independent variable and dependent variable is not always linear, meaning one increases, one decreases. Sometimes the relationship is more complex, and you could look at this relationship here and say, there is some relationship. It's a strong relationship. Well, it's not strong. It's R equals 1.8. There is a relationship, but I'm not really seeing it, or I'm not really expressing it correctly. So you all know with a dose of a drug, sometimes a drug has a threshold. So the drug will work, alleviate pain, and then just stop, right? It thresholds out, it flattens out. So we have to find a better way to describe that relationship. So we just want to know that if we see a scatter plot that looks awkward or looks like something's going on, but we want to investigate more, we have to question and say, is the relationship we're looking at actually a linear one, or is it a relationship that is not, but still has value and still has something that we need to explore? So you want to think about understanding variables, right? And relationship studies versus a prediction study. So in a relationship study, the researcher looks to gain insight into what are the relationships between complex variables. And the first phase is really, even in experimental design, is knowing what to hold constant. So we tend to look at a correlation matrix, which looks at how the variables relate to each other, which variables are highly correlated, mean they work together well. So income increasing with education, that's a strong intercorrelation. We can look at the strength of the relationship, and here we can look at significance. So are the changes we see amongst those two variables actually significant? And this will make sense the more we see it, but you'll see why when we do a correlation matrix, we only fill out half. So let's think again about significance. We want to know, is the relationship we're seeing, once we get the R value that tells us the strength of the relationship, we want to know, is that relationship also significant, right? If there's no significance, the relationship, the R value is not really, does not really matter. So the null hypothesis would say there's no relationship, that when I'm looking at two variables, the hypothesis is that the R value, the Pearson's correlation coefficient, equals 0. But we're going to test and see, are there relationships in those variables? And here, if we think about this, if we look at the relationship of 2 and 2, 1 and 1, right? If we only fill out this half of the table, because if we did this part of the table, we have 4 and 1, and here we have 4 and 1. So just think that this table, if we completed it, it would just repeat itself. So which are the strongest correlations here? Are they positive or negative? And then are they significant? And describe this relationship in a sentence. So what I would do first is look at the magnitude, right? The weight of the largest number. So when I scan through, I see there's a 59, okay? 59 refers to absence of lower extremity hypertonicity, and 7, which is functional skill mobility score. And is it positive or negative? It's positive. which means for those who don't have lower extremity hypertonicity, they're going to have a higher functional skill score. So less of this health issue or less of this functional issue, they're going to have a higher score. It's also significant if we look here, right? P at the 0.2 level. So it is here, their significance levels are odd. This should actually be 3-star, but this is highly significant, right? Anything less than 0.05 is good. 0.001 is the actual best. So this is the strongest relationship. There are some negative relationships that are significant. There are some more positive relationships. So try this for yourself a bit, right? Interpretation is key. So think about this, right? This is the recap of Pearson's correlation coefficient, or R. It indicates just the strength of the relationship. If we get a 0, it means there might be no linear relationship, but we need to look for nonlinear relationships. And that the stronger it is, either positively or negatively, toward positive or -1, the stronger that relationship is. We need to use the correlation coefficient variables at all levels. So nominal, interval, ratio, right? We have a lot of freedom in the way we use this. We assume the normal distribution and that each score is moving around the mean. Now let's look again at another example. This looks at proximal and distal function. All right, I've circled a score. And this is the Pearson correlation coefficient. Many times we round up. Let's just say we didn't here. We know that R equals 0.365. So if we scroll back, sorry to go so fast. 3, okay, so it's a fair degree, right? A fair degree of relationship. Okay, let's come here. I'm sorry about that. Fair degree of relationship, positive, so as it would mean that when one thing increases, another increases. But look here, look at the significance. I'm sorry that it's covered occluded a bit. It's 0.121. This is non-significant. So although it looks like there's some fair level of correlation, what the significance level tells us is there's no relationship. And what the scatter plot tells us is the same thing, that while we may look like there's a line, there's really a lot of like points on this graph that don't make sense. So there is no relationship in the visual scan and the scatter plot. It looks like there might be a fair association or correlation, but since it's not statistically significant, there is no relationship between proximal and distal motor development for this sample. And that if you can't, let's say that you say, okay, so I can't use Pearson's correlation coefficient. If you have ordinal level variables, you may want to use Spearman's rho. So this is why level of measurement matters. You know, for nominal or interval ratio, you can kick in your correlation coefficient, but if you have ordinal level variables, you're going to use Spearman's rho, which is the equivalent. Here's another example looking at Spearman's rho. We're looking at verbal and reading ranking. So what's the relationship between verbal scores and reading scores? Here we have a strong relationship, a pretty strong relationship, maybe 0.794, 0.8. It's significant, you know, with 2 stars, meaning at the 0.01 level. And it looks to me like it's a positive relationship. So as, you know, reading scores increase or verbal scores increase, reading scores increase. And if you think about this from a developmental perspective, right, it's why people encourage reading to children and reading and being verbal, that those things might work together. And here we see the relationship is a strong relationship. It's a significant relationship, and it has a positive correlation on the scatter plot, right? So it looks pretty consistent. Oh, So questions, right? I know we covered a lot. Think about what's the difference between association and correlation? What is a positive and a negative direction look like? What is the hypothesis for correlational work? And the how would you phrase it? And then when you look at the tables, how can you pick a correlation coefficient, either Pearson's R, Spearman's rho? How can you tell that the direction? How can you tell the magnitude of the change? And then how can you tell if it's significant? So just questions to think about. And I will reach out to you in a few minutes and do your second video for this week.